Yule is one of the first more complex features of Solidity that you'll start to dive into as you transition from a beginner slash intermediate smart contract auditor or Solidity developer to a more advanced Solidity developer slash auditor. And being able to use Yule, knowing how to sort of interface with it and manipulate memory at a low level can actually give you superpowers in some distinct edge cases where you can actually pull off an exploit or see exploits that a version of you that didn't understand Yule and low-level memory manipulation would not be able to see. So in this video, we're going to go over some very low-level manipulation of memory in Yule, and we're going to take a look at a very cunning finding that utilizes low-level memory manipulation in Yule to actually pull off an attack. Okay, but first of all, before we get into it, why should you listen to me about advanced attacks or Yule or anything like this? Well, my name is Owen, and over a year and a half ago, I founded Guardian Audits, and ever since then, our team has uncovered dozens upon dozens of critical and high vulnerabilities uncovered from auditing over, several hundred smart contracts and 1,000 hours spent auditing. And my goal with all of these videos, and especially this one, is to distill down everything learned from those hundreds of smart contracts audited and those dozens and dozens of vulnerabilities found and give them to you so that you can ultimately become a much better smart contract auditor than I ever could be in a fraction of the time. So without further ado, let's get into this video about low-level memory manipulation in Yule. Okay, great. So we're going to start off by just covering some high-level basics of how memory is managed. And then we're going to actually go in and sort of play around with things. And then we're going to take a look at a very interesting exploit. And we're actually going to code it up live. We're going to code up the exploit contract, and we're going to walk through it, and we're going to see just how cool low-level memory management can be. So the first thing we need to understand is that memory is split up into words, right? So these things called words. Now, the way you can think of it is that there are sets of words like each of these, and these are all a bunch of bytes, right? So let's say I have one word here and it's just a bunch of bytes. We have 0, 0, 0, 0, and it goes on until we get to the end of the word, right? And then let's say I store, maybe this is the free memory pointer, which we will talk about shortly, and there is a OX40 stored here. And so each word has 32 bytes. And just a refresher to remind yourself is a single byte is a set of 2 hex characters like this. So if I take this out and we extrapolate this as hex, if we have a 4 as a hex character, then we have a 0, 1, 0, 0, right? So we have 1, 2, 4, 8 for these individual bit values here. And this makes up a 4. And then immediately to the right of that, we have a 0, which is, of course, 0, 0, 0, 0. This makes up a 0. And then right here, we have 1, 2, 4, 8. And then this becomes 16. We have 32. And we have 64. So when we have an OX indicating that this is just hex, this OX40 here is actually 64, right? So this is equal to 64. So what we have stored here in this sort of like memory slot, this word, we could say this is the first word that we're talking about here, is OX40, which is equal to 64 in decimal format. So then there can be other words that are stored in memory. So you can have the next 32 bytes here. And this could be anything. It could be A, 1, F, it goes on and on. Just any arbitrary bytes, right? And it could just fill up all of these 32 bytes. So you have all these words. So the structure of the storage of memory here is made up by these 32 byte words. Now let's talk about some of the inherent structure of memory, because like I quickly mentioned here, you could have something called the free memory pointer, and it actually points to where it is safe to add memory. So let's figure out, what is a free memory pointer, why is it only safe to add memory in a certain spot, and what is the general layout of memory, right? So in each of these word slots, you could actually have a corresponding sort of hex reference to each word spot. So we could have 0x00, which would be the first spot for a word. And then what's going to come here is, here's your first word, right? And we could say that this is just like we had above, a bunch of zeros. And then, this word is just full of arbitrary bytes, we'll say. So arbitrary 32 bytes right here stored in 0x00. This is the first word slot in memory. And then, of course, there is, can you guess what the next slot is? It's going to be 0x20, right? Because if we come back and we look, here we had 40 was 64. If you just had 20, it would be a 1 here and a 0 here. This would be 20 and it would be 32. So when we say 32, this is our, so if we're talking about bytes here, this is the first byte. If we have a 0 here, this is the second byte. And then it goes on and on and on until you reach the full 32 bytes. And then you come into the second word as soon as you hit the 32nd byte, right? And then now we're here and we have another 32 bytes, another word. These are fantastically written out here. So anyways, these first two sort of word slots are actually sort of considered reserved for Solidity to actually use as scratch space. For example, when they're executing some functions, those functions will actually go ahead and use this scratch space, which is expected to be, clear and not used in an actual program to compute, whatever the necessary computation of that function is. So Solidity sort of expects the user to steer clear of these first two, word slots. And so that motivates what is stored at the next slot, which is 0x40, right? So everything up to, it would be up to this last byte here, which would be 0x3f, is going to be basically reserved for the EVM really to have scratch space. And then as soon as we get into 0x40, now we're talking about the free memory pointer. So this particular word is, of course, another 32 bytes. I think I'm getting a little bit better at writing bytes. It's hard to tell. We'll get there. So on this 0x40 word slot, what we have is, like I said, the free memory pointer. So this is another word of bytes, but it is a special word of bytes in that once you get all the way down to it, it's going to be at first initialized with 0x80. And I made a mistake here. This would be, 0x80, whatever. So this is initialized with 0x80. What does this mean? This means that what this word slot is telling us is that it is safe to write memory to the word slot that is at 0x80 right at this moment. This is what the free memory pointer does. It tells us where we expect memory to not be, right? So if we've written up to, some word down here, could be 0x80, A0 could be, some future word. If we've written to all the previous words, then OXA0 would be here in this free memory pointer word. If I wanted to write memory and I said, okay, in which word can I write this memory to without overwriting something I've previously written in memory, I can go and I can basically look at this OX40 word, see that it is, OXA0, whatever the word is, and then say, oh, well, I can go and put my memory here in this word, and I know that I'm not going to be overwriting anything. So right now it is OX80. Why is it not OX60, right? So OX60 is, of course, the next word that is going to be available. This is another 32 bytes. I'm not going to keep playing myself like that. So, of course, we have, a bunch of bytes here. This is actually intended to be the sort of zero space. This is supposed to be blank and empty for this OX60 word. So this is actually used as like the initial default uninitialized value for things like a dynamic array. It needs to have some sort of null value, and that is exactly what OX60 is going to be used for. So this is exactly why the free memory pointer at OX40 is sort of hopping over OX60 and saying, look, you can write memory here at OX80. So this is the first place where the free memory pointer is going to basically allow you to write to, or tell you to write to, really. If you're using Yule, you can write anywhere you want, which is quite dangerous. So of course this will be a completely uninitialized, there won't be any bytes here to be overwriting. And so this now, when you start writing to memory, which we're going to do in just a second, you will want to start writing to the OX80, whatever stored at the free memory pointer here. Okay, great. So here's our high level, beautifully drawn overview of how memory is laid out, right? So again, we have our scratch space from OX00 up to OX3F, and then OX40 is the free memory pointer, and then at OX60 we have just a zero null value, and then on OX80 and beyond it is completely whatever the user wants to write to memory. So let's quickly just go and mess around. Let's play around with some memory, some im storing, some im loading. Let's see what the free memory pointer is, and let's basically just get our hands dirty, right? So we'll start off with an assembly block. Let's log what the free memory pointer is so we can really feel it, right? So we can see, okay, that is what the free memory pointer is. So first of all, we want to grab the value of a word, right? So this is going to be a bytes 32. So this is going to be word free memory. This is what I'll call it. And then what we can do inside of our assembly block is we can do word free memory, and we can assign it with this operator here, the walrus operator. And what we can do is we will want to imload at OX40, right? So we're imloading what is stored at this word here, which is the free memory pointer. So we'll get this value here, and I'm claiming that this is going to be OX80. And so what we can do is we can console.log bytes 32 word free memory. And now if we go ahead and compile this, we get no errors. We can go ahead and deploy this. Let's just clear these, deploy it, and let's run our test. Let's see. And there's our console log. We have a bunch of zeros in this first word, and then 80. So that's exactly our free memory pointer, right? So we've loaded in what's at the free memory pointer, and we're seeing that it's 80. And then, of course, we can also look at OX60. We can compile that, deploy that, and come here and see that OX60 should be empty, and it is. Okay, great. So if we get the free memory pointer, now let's say, what if I want to write to memory, right? So if I'm going to write to memory, of course, it is always a good idea to look at the, right at the free memory pointer. So we can actually just make we can call it the free memory. That's what we can do. Make a little variable for it, and let me just clear these. And then, so let's say, what do we want to write here? Let's go ahead and store. So this is writing to memory, right? Storing in memory. And we're going to write it at the free memory pointer. And then let us put 32. So I'm writing it in, this is a decimal here. We're going to see it show up as 0x20 in hex. And so let's deploy this and let's run that. And we can actually use a very cool debug here. And let's see, let me just minimize this stuff. We'll go to memory and let's see. Let's go, before we do any of that crazy logging. Okay, cool. So we are right before this store here. We can see the layout of memory right here, right as I've drawn it. My drawing is a little bit better, but that's fine. Remix does a fine job. The first slot here, of course, here's the scratch space we're talking about, and then we can see this is exactly the free memory pointer. Now if we go forward a little bit, now we can see some more stuff has arrived, right? So exactly when I got my free memory pointer, this gave us back what was stored at 0x40. 0x40 gave us 80, and then now this is a pointer, remember? This is saying, where do we want to write to? Now when we're storing, we want to write to that 0x80. So exactly, now we can see we skipped over 0x60. That's the 0 word. And then we go to 0x80. And if we read 0x80, we can see it is exactly 20. And of course, if we go into a Python shell, we can see if we write this as a string. So if we have 20, and then we want to cast that back down to decimal, then it is 32, right? So I put 32 in, and we can see our 32 value being stored at where the free memory pointer was. Now it is something we want to note is that this free memory pointer here is actually going to be the same. So if I actually just load 0x40, and we're going to be printing this out. So even after I stored to that slot, if I go ahead and let's clear this, deploy this, then we can see if I run this test function. So now we can see if we get the free memory pointer after we did this store and then we log it again, then we can see that we actually are still pointing to 0x80, right? So that's actually a problem. It's very important to note that if you store, you are not automatically going to update the free memory pointer, right? So the free memory pointer is supposedly supposed to tell you, okay, where have we already written to and where should I be writing to now to not overwrite any previous data. But if we go ahead and debug this again, we just see, let's see, and I go forward a little bit more. Here we go. We can see right at this point in time, we can see that there's an issue right here. We can see that the free memory pointer is 80, but we actually have a value of 80. So if I try to write something to the free memory pointer again, I'm going to overwrite this value. So this is something to note. When I am storing, I'm actually writing stuff. It's not going to automatically update the free memory pointer for us. Of course, if you're just using high-level Solidity, this is going to happen. They are going to write that for you. But this is something that you should be aware of if you're using low-level memory manipulation like this. You will need to update the free memory pointer after you do any sort of store if you expect to be able to use that free memory pointer later on to write something without overwriting what you just wrote, or also if there's more solidity that interacts with memory after this assembly block, you will definitely want to update the free memory pointer for that. Okay, great. So we've started manipulating memory at a really low level. Now let's look at a really interesting case, which is the storage of a string. So we'll do string memory and we'll say hello. And so you'll notice that whenever we write strings, we use the memory keyword here inside of a function. So that means that this string is stored in memory. Let's have a look at exactly what the string looks like in memory. So what we can do is we can actually just ignore all of this, and really we can just go to the debugger. So what we'll do is make sure that's compiled, add our semicolons, add a name to the string, and then we'll run that. Good to go. Here we go, we run test, and then we hit debug, and here we are. Let's have a look at memory, right? Okay, so here we haven't written anything to memory yet. Now we go along, here we are. Now we go a little bit further to get everything. There we go. Okay, so at this point we can see the free memory pointer was updated, right? Because we're not using low-level manipulation to store this string here. We have at 0x80, we have just the value 5. And then at 0xa0, we have the value that looks unintelligible, but it actually stands for hello in hex. So why do we have this value of 5 here when we just wrote the string hello? Well, this value 5 is basically telling you how long the string is. So 5 means 5 bytes. So if we count here, we go 1, 2, 3, 4, 5. There's 5 bytes, and that is how long our hello string is, right? We've got 1, 2, 3, 4, 5, 1 for each character. So now that we've seen how a string is stored in memory, let's get on to the interesting bit. Let's see a really cunning attack vector that actually utilized low-level memory manipulation to incite the attack. All right, so let's have a look at this system that I've created to sort of recreate a version of this exploit. We have a rewarder contract, and essentially this allows anybody to give a reward to somebody else, and then that person can pull all of their rewards at once in a single for loop. Terrible idea. And ultimately, the interesting bit here is that when we do a transfer, we catch any revert reason, the bytes for that reason. Then what we want to do is we want to parse it and then emit an event, maybe so somebody could debug the transaction or something like this. And so in the get revert message function, we are actually, this is the function that introduces the critical exploit here. So I'll give you a minute. Maybe you can already spot it. Maybe you can see what the issue is going to be. But if you couldn't spot it, I don't blame you. It's a very cunning attack vector. And I have to give all credit to, I think, LLL and OX Deadbeef, who found this exploit on, I think it was a Sherlock contest. And yeah, it was a fantastic exploit, as we'll see shortly. So if we get the revert message here, and essentially what we're looking for is we get the data from the revert, and then of course if it's perhaps a panic, then we just return no string. There's no string to be parsed. If the error selector matches an error that has just a string, then we're going to go ahead and basically attempt to ABI.decode this data into a string. So what are all these low-level assembly blocks doing? First of all, what we're doing is we're grabbing from the data the first word, right? Remember OX20, if we convert that, grab it right here. If we convert OX20 to decimal, we get 32, right? So 32 bytes, this is the first word. So we're getting an offset of the data, and this is going to basically give us what is sitting exactly at the error selector that is from the data. And so that error selector is, if it matches this error string, then we're going to attempt to parse stuff, right? So in this assembly block, what we're doing is we're taking the data and then we're reassigning it, we're shifting it by literally 4 bytes to be exact. So 4 bytes is what we're shifting this data by. And why are we doing that? Because this error selector, if we go ahead and count, is 1, 2, 3, 4 bytes long. So what we're doing is, once we get the error selector, which is sort of just prepended onto the data here, we just sort of like splice that error selector off to get the clean data that can be used to actually decode this string here. So the key to this exploit actually comes from what we just saw when we were examining how a string is stored in memory, right? So you'll remember the string had that 5 there that was indicating that that was the length of the string. Now what we can do is we can have a string that says it's very long, but actually doesn't have a whole lot there to actually back it up, right? So we don't need to actually generate a really huge string to actually have this decode call actually go ahead and think that there's a really huge string to decode and actually go ahead and try and decode all of it, try and iterate over the entire quote unquote string, ghost string that isn't even there, and spend all that gas and ultimately out of gas revert because they're trying to decode such a huge string. And so what's the ultimate effect of this is that when we attempt to get revert message for a token that is a malicious token that does this, then what we'll end up doing is actually, instead of being able to catch this and then just move on to the other tokens and get all of their other rewards distributed, what will happen is the transaction will just run out of gas because we'll be trying to decode some huge ghost string and there will be literally no gas left to do any other iterations of this loop or literally anything else afterwards. So that is the exploit here. That's the idea. Now let's see what it looks like in practice with a malicious token contract. So what we want to do here on the transfer function, when this gets called, we want to revert in a very special way, giving it exactly the bytes that makes it look like this error selector with a specifically engineered fake string that pretends to be extremely long. So let's get right to it. So we'll start off with our assembly block. And the first thing we want to do is, of course, we want to get our free memory, right? Our pointer to the free memory spot, right? So what we'll do is we will load OX40, see where we can write memory without potentially messing anything up, even though in this case it will be OX80. And then what we'll do is we'll start off by storing. We want to put at the free memory position, we want to put a word that starts off with this error selector very cunningly and then is basically padded to the right until what we want to create in the next one, in the very next word, and we'll see what this looks like in the layout when we go ahead and debug this, is we want to have the information for our string be in the very next word offset by just 4 bytes, which is going to be that error selector. Remember, we need to offset things by 4 bytes because this get revert message function is sort of slicing the data by this 4 bytes. So we'll start off by grabbing this error selector and we want to make a whole word out of it. So to make a whole word, first of all, we have 4 bytes here already. Now we need 28 more bytes. So let's strap in and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So this should be a full word that is starting with our error selector here. Okay, so now what we need to do is we need to store at an offset of the free memory pointer. Remember, we have to offset it by 4 bytes. We're going to store an offset for our string here, and I actually don't need the semicolon. And the offset is going to basically point to where the information about our string begins. So then what we're going to do is, essentially, this is exactly where the exploit comes off, is when, just like we saw, when you have information about a string, it starts off with the length of the string, and then the string comes in subsequent words after that. So what we have to do is get, of course, remember, so we're going to be in the next word after this, but we're going to be offset by 4, right? So 1 word plus 4 is going to give us 36 here. And then what are we storing? We're storing the length of the string. So what we can do is we could say, yeah, our string is this long, except don't worry about the actual string. Just take us on our face value that the string is actually there, right? So immediately after we do this, we can essentially just revert with all of this data and let it think that there is actually going to be a string after this word that spans for that length. Okay, so now we are literally ready to revert. And then now we can see if we actually go ahead and let us also get a contract good token is ERC20, and we'll make a constructor for this one, constructor, and we'll do ERC20. Good. Good token. You should buy it. And of course this needs to be that assignment operator since we're in Yule. And then let me just throw away all of this. Let us deploy a few contracts. So we have a good token, a malicious token, and then we deploy the rewarder. So let us say that I want to reward the user. So I have to take the user address here and then take the good token. I give them 0 good tokens because I don't have any tokens, don't want to really deal with giving myself tokens. And then the user withdraws, we can see it successfully goes through. And then now if I take the malicious token, if I want to do the same and just copy this malicious token, give the user 0 malicious tokens, then we try to withdraw, of course it will revert. And it's going to revert on this decode call right here because we're seeing some impossible infinite string that is attempting to be decoded, right? So we can even more closely sort of prove this to ourselves that we are decoding, and then of course we can console.log after we get this, so console.log decoded, and then we can see if we get to decoded, we should not be able to see decoded, but we should be able to see decoding. So if I go ahead and compile after adding these logs, and then we find the rewarder, and let's deploy that, then we will take the user address here, and we'll go ahead and get the malicious token here, and give reward of 0 tokens, and then withdraw reward. So we're decoding, and then all of a sudden we end up with a revert, and we never end up seeing decoded. So we're never able to successfully finish this decoding of this massively long string because we essentially just run out of gas, right? And we can actually check out exactly what the memory looks like here if we go and debug this transaction, and we just slide it until we get about, so right here this is perfect. So what we can do is I'll scroll down and we'll check out the memory. So a lot of stuff going on here. So we can see in the scratch space, we can see clearly there's something going on. Solidity is using the scratch space here. We have our free memory pointer, and then we have a bunch of other things in memory. And what we're looking for is our error selector here that we stored in this word here that is being stored in this data memory here. So we're looking for this pattern here, and we see that in OX120. We see the error selector here. And then we can see our offset in the next word. Here is our OX20 offset, which would then make this 1634 and then continued into this one, into this word. This is our length, right? So everything is jumbled up. It's not exactly in each word because remember we shifted everything by 4 bytes to add in this error selector here. So we have 4 bytes for the error selector, and then exactly when this assembly sort of shifts things and basically pops off these 4 bytes, then what we're left with is a first word that will end in OX20. And this is our offset. It's going to point to where the actual string is. And then we have in the next word, which will be OX140, will be entirely just this this bytes number here, which is saying exactly how long our string is, right? So if we were to draw this out in as slots, we have this slot here, which is OX120. So in OX120, we have the first 4 bytes. This is our error selector. So this is OX08C, OX, and continue. Those are the 4 bytes of our error selector, and it ends with an A0, right? And then we have a bunch of 0, 0, 0, 0, 0. And then in the next word, in OX140, we have 4 bytes here of what is basically a little bit of padding, and then we have this OX20. So if we count 1 byte, 2 bytes, 3 bytes, 4 bytes, that is exactly what's going to be here. So you have 0, 0, 1 byte, 0, 0, 2 bytes, 0, 0, 3 bytes, and then this last byte is going to be 20, right? And so what's going to happen is when we shift this by this 4 bytes here, when we basically say this gets sliced out of here, then this bit of this OX20 is going to move up to the end of the next word, and then all of this is going to basically shift over, right? So really the first word becomes OX20, and then the next word, it's OX140. We'll see what's happened is our length has been split. It's split in OX140 and in OX160. So what's going to happen is you'll notice that we have those 4 bytes here, 1 byte, 2 byte, 3 byte, 4 byte, plus this should be our entire length. So if I go ahead and take this into a Python shell, and if we do this base 16, so we have that number, and then we add on the rest of what this ought to be, so 1 byte, 2 byte, 3 byte, 4 byte, and we put that in there. Here's the full number, and then if we hit enter, there's our length that we put in down here, right? So what's going to happen is that full number is going to get shifted over until all of these bytes, this bytes that was chopped off is now shifted up into OX140, and now OX140 is going to be entirely just for the length of the string. And then after that, we can clearly see that there is actually no string that's there, and that's really the crux of the exploit. So that is a very, very cunning exploit that can be pulled off with some low-level memory manipulation in Yule. I hope you learned a few things. I hope you thought that exploit was really cool. I certainly did when I first saw it. And I hope most importantly you got a little bit more comfortable with Yule and assembly and the way that memory is really laid out in the EVM. If you're looking for a fantastic community to continue to build on what you learn and make connections with others who are trying to grow in the space as well, and even potentially team up and compete in team audits and earn prizes for vulnerabilities that you uncover while working with others and getting to know their process. If that sounds like something that you'd be interested in, then head over to lab.guardianaudits.com and go ahead and submit an application to join our community of over 500 now smart contract auditors and people who are interested in Web3 security. And lastly, of course, if you're still not 100% confident in your Web3 security skills, I collaborated with several other top-tier security professionals in the field to bring you exactly what you need, which is an extremely efficient course that takes you from basic Solidity knowledge to being a complete smart contract hacking pro in as efficient as possible of a manner, with hours and hours and dozens of hours of lecture content with dozens of exercises with recorded solutions and walkthroughs for you to be able to get there as fast as possible. So if you are looking to go the paid route, and that's something that you do want to do to really accelerate your learning, then of course feel free to take $50 off when you buy the Smart Contracts Hacking course in the description below. Okay guys, that is it for this video. I will see you in the next one.